Hi everyone. This script was made by Yohei Kawaguchi, and this speech was generated by TTS. I will talk about DCASE 2021 Challenge Task 2, Unsupervised Anomalous Sound Detection for Machine Condition Monitoring under Domain-Shifted Conditions. This task organization was a collaboration with these members. Anomalous sound detection is the task of identifying whether the sound emitted from a machine is normal or anomalous. Automatic detection of mechanical failure is essential in the Fourth Industrial Revolution, which includes artificial intelligence-based factory automation. Anomalous sound detection has two challenges. One is how to detect anomalies without anomalous training data. We can collect normal training samples easily, but anomalies are rare in actual cases. It is impossible to collect all anomalous variations. So, in many cases, we can use only normal data in the training phase. The other challenge is how to avoid being affected by training test gaps. Seasonally or accidentally, the recorded sound can change between training and test data regardless of whether it is normal or anomalous. For example, in this factory, the demand for cakes changes, depending on the season. In this case, the speed of the production machine changes, and the sound also will change from training to test. This training test gap is called a domain shift. It is difficult to distinguish between domain shifts and anomalies. This figure shows the position of this year's challenge task. The x-axis means fewer training samples of events to be detected, and the y-axis represents more significant domain shifts. In the upper left, there were some past tasks of few-shot event detection, but these tasks were to detect defined sounds. The 2020 task 2 was in the upper right. In that task, we targeted unsupervised anomalous sound detection, that is, the detection of unknown sounds. This year's target is in the lower right, unsupervised anomalous sound detection under domain shifts. This year, we prepared 7 machine types: fan, gearbox, pump, slide rail, toy car, toy train, and valve. Each machine type contains 7 sections. A section is a unit for calculating performance metrics. It's almost a machine product and similar to Machine ID in the 2020 version. Each section consists of 2 different conditions, called the source domain and the target domain. The operating speed, machine load, and so on, differ between the 2 domains. We made the dataset from Toyota's 2 and MIMI DUE. Training data in source and target domains contains 103 normal clips, respectively. Each clip is a 10-second monaural wave file. The 2021 task setup is similar to 2020 but with some differences. First, 1,000 training clips were available in the source domain, whereas only 3 were available in the target domain. The official score was then defined as the harmonic mean of AUCs and POCs over all machine types. Finally, in addition to the anomaly scores, we required submission of the decision results. However, we did not use it for ranking. We prepared 2 baseline systems. One is a regular autoencoder, and it calculates the reconstruction error as an anomaly score. This baseline assumes that reconstruction is difficult for unknown sounds and that they are anomalies. The other baseline is an outlier exposure-based detector using section classification, and it calculates the negative logit of section classification as an anomaly score. This baseline assumes that section classification is difficult for unknown sounds and that they are anomalies. We received 76 submissions from 27 teams. 20 teams achieved better performance than the baseline systems. This figure shows the ranking of the target domain AUC scores up to 10th place. Each team had its own strength-weakness for a particular machine type, but the target domain AUC roughly correlates to official ranking. Here, we have questions. What's an approach of the top rankers? What's a new finding in this task? We found 2 distinctive approaches in the top rankers' solutions. The first is a parallel type hybrid method, developed by the 1st, 4th, and 5th ranked teams. This approach is an ensemble of inlier modeling based outlier detection and outlier exposure. Here, inlier modeling is defined as a method modeling normal condition data and detecting outliers. This parallel type hybrid uses multiple models in parallel, so it is likely to achieve high performance for generalization. However, we must note that the overall model tends to be significant due to ensemble. The second approach is a serial type hybrid method, developed by the 2nd and 3rd ranked teams. First, this approach trains its feature extractor by using the section classification task. The trained feature extractor then extracts a feature embedding and sends it to an inler modeling-based outlier detector. This approach uses powerful feature extraction specific to outlier exposures, but the robustness of inler modeling overcomes the instability of the outlier exposure. This approach can limit the model size. Also, we can perform domain adaptation by updating IAM with only a few target domain data. However, we must note that section classification does not always provide good embeddings. There are many future works. That's it. Task 2 related 7 papers will be presented in the workshop. Let's enjoy the discussion.